everyone. My name is Matteo Marangon. Thank you for having me here presenting today, and thank you also especially to Eno Brands and Scott Labs to allow me to present this overview on the protein stability in wine here today. So to start introducing the topic, we need to go and familiarize with the culprit. So what is responsible for protein instability in wines? So the proteins of grapes. And in particular, we know from techniques, analytical techniques like the one displayed in this picture, which is a sodium uracil sulfate page, so electrophoresis. So technique that allow to separate proteins based on their molecular weight. So this is a typical protein profile of a juice in this case, but in wine it's quite similar. In this case, we're talking about a Semillon juice. And you can see that the proteins that we find in juice and then in wine are only a few. And namely, we talk about invertases, glucanases, chitinases, chromatin-like proteins, also for simplicity named TLPs, or lipid transfer proteins, LTPs. So the protein profile, as I said, is quite simple. We have only a handful of proteins, but not all of these proteins are heat unstable, so not all of them contribute to the problem of protein instability. So those that do contribute are the glucanases, and most importantly, chitinases and chromatin-like proteins that incidentally are also those with a thicker band. So they're also those mostly found in juices and then in wines. So these three proteins that have something in common. They are the so-called pathogenesis related proteins. So proteins related to the pathogenesis. So proteins that the plants, so the vines, produce to protect themselves from fungal attacks. So they're proteins with an antifungal activities. Other characteristics that make them similar and make them a problem, because they are those responsible for the instability later on in wines, is that they resist, so they're quite strong, they resist to proteolysis, they are stable at low pH, so typical wine pH on around 3 to 3.5. But these proteins, that they are so stable during vinification, they tend to become insoluble during the wine storage, especially that is carried out in temperature conditions which are not optimal. So they tend to become a problem, and they are basically the target of all the studies aiming to understand the protein instability in wines. So a very simplified version of what happens, so the mechanism of haze formation in wines. So if we have a wine after bottling that has been filtered, which results clear, limpid, we still have in wine, if they haven't been removed beforehand, proteins which are soluble, the ones that I mentioned in the previous slides, and particularly the PR proteins are those that can cause trouble with time, because these, as I said, they tend to become insoluble during storage. So they lose their solubility, they become insoluble, so they flocculate, aggregate, and eventually they form a sediment that is, of course, visible as a turbidity and is not appreciated by consumer. So the question here is, so the approach to study how this happens and to understand the mechanism is to have a look what's inside this turbidity. So what is that became turbid? Oh, sorry. So we talk about the proteins that are found in natural wine haze. So when you look at this turbidity and you separate it by centrifugation, you can separate and have a total wine, the supernatant, so what you result, the clear part of the centrifugation, or the pellet, so the turbidity itself. And if you run another gel, you can see that similar bands are there. This, I remind you, this was the glucanase, this is the chitinases, and this is the TLPs. So you can see that in the pellet, so in the turbidity naturally formed in wines, we still find all these proteins, but especially chitinases, chromatin-like proteins. So those are the responsible one, the one causing this problem. So occasionally we do find also glucanases, but It's less in quantity in wines, and so it's kind of less of a problem because it's also not so strong during fermentation, so it tends to naturally precipitate out during fermentation. But chitinases is always responsible, and somatin-like proteins not always, because as we will see later, there are different somatin-like proteins, some that are stable and some that are unstable. So the thing is that when heated, so these proteins, they undergo a change, and the change has to do with their three-dimensional structure. So proteins are normally folded into a 3D structure, which keeps them soluble in solution. So if you heat them up, and this is also part of long storage, especially if in wrong condition, chitinases, they basically lose their three-dimensional structure, they unfold, and this is an irreversible step. So they unfold, they open up, and they can't return back to the original state. While somatin-like proteins have been shown, most of them, they do unfold, but if you cool them down, they refold. So they come back to original state. So it's two different mechanisms which differentiates the two main classes of proteins involved in haze formation. So to elaborate a bit more on the mechanism that I've shown you a couple of slides ago, we can see now this is a somatin-like protein. This is a three-dimensional structure. You can see that it's nice and globular in native state. So it is three-dimensional, and in this case, it is soluble. So if you have that in your clear wine, after bottling, the wine will appear soluble. They pass through the filters, so you can bottle proteins as well. But the first step, so what starts this cascade of events that eventually leads to a turbid, to a hazy wine, is this unfolding, refolding of proteins that I mentioned before. So this destabilization of the three-dimensional structure of proteins. And this is a step mediated by temperature. So the higher the temperature, the faster the steps happens. Once the proteins have been unfolded, so they have been damaged, the three-dimensional structure, they are kind of in an unfolded state, which is open. And in the inner part of the proteins, there are many hydrophobic binding sites. And this leads to protein self-aggregation. So unfolded proteins, via hydrophobic attraction, they can attach, combine with each other, they can aggregate, and this leads to an increase in size. And also to prevent the refolding. Once they start aggregating, they cannot get back to the original state, as some somatin-like protein can do. You can see here the green arrows of the refolding step. Once this mechanism has started, so when you start having protein self-aggregation, then other components in the wine matrix, they enter into this mechanism, and they basically cross-link different aggregates, different protein aggregates. And it has been demonstrated that molecules that we find in wine, like sulfates, salts, metal, phenolics, they can take these aggregates of different size of proteins and kind of combine them, do this cross-linking action, which makes the particle, insoluble particle, bigger. And when it becomes bigger than 1 micron, or micrometer, we can actually see it at the naked eye, and so the wine becomes visibly turbid, visibly hazy. So this is all part of a series of studies that has been done to define the mechanism, to really understand how this works, because it is essential to know these steps in quite high level of detail for two reasons. One way is to set up better predictive tools, so to predict the haze potential of wines, so your heat tests, for example. And the other side, by knowing what's happening at different stages, one can think of targeted techniques, alternative to the current solution that we will see in a second, of protein haze prevention, so bentonite use. So techniques that will hopefully lead to a replacement of bentonite, or at least a reduction of its use. So the first part is that most predictive tests to predict protein instability in wine, they lead to overfining. And we know that now because of the studies we've done. So typically, I don't know, in the US, what the most commonly used heat test is, the conditions, but typically we talk about 80, 90 degrees heating. to destabilize the protein, followed by a cooling period, which allows for degradation, and then you measure turbidity before and after. This is a typical heat test to predict protein instability. But the heating is normally done at temperatures which are far too high. So they are destabilizing not only the unstable proteins, so your chitinases, your chromatin-like proteins, and your glucanases, but also the other wine proteins that would be stable otherwise and would not contribute to haze formation. So if you destabilize all the proteins, all of them will contribute to the turbidity form upon heat test. So all of them will be accounted for when you start deciding how much bentonite, for example, you add. And we know that because upon individual purification of the different classes of proteins, we could assess, we could quantify the temperature required to unfold them, the so-called melt temperature. So we know that chitinases, if you heat them, the wine at 55, they unfold already. Chromatin, depending on the type of chromatin, some they unfold at 56, some at 62. Beta-glucanase is much more sensitive to heat, so already below 40 you can unfold it. While other proteins that are found in wine, invertases, lipid transfer proteins, they are stable ones. They don't contribute to haze formation in wine, and in fact their melt temperature is above 80. And this means that when you do a heat test at 80 degrees or even more, you see a turbidity generated also by proteins which normally are not a problem. So you overfine, you tend to overfine your wine because you want to remove these proteins as well. So proteins, of course, have been are the main part of which is studied in the study of haze formation and in alternatives. So we know a few things now about proteins. We know that they are positively charged, the wine pH. Well, that has been known for a while. We know they are very stable, a low pH. We know that they are robust. They're globular. This is two chromatin-like proteins, three-dimensional structure. This makes them also resistant to proteolysis because an enzyme struggles really to get inside this tight structure to cleave some of the bonds, so to break it and to destabilize it. We know that they can be destabilized by heat. So heat-mediated unfolding has been shown. Different proteins have different heat requirements. And we know that they tend to get insoluble during wine storage. So all of this information, which has been collected over a couple of decades of intensive research, can be used to remove them, to get rid of them in a more targeted way that it has always been done. So, for example, the fact that we know since a long time that proteins are positively charged, so they have a surface charge which is positive at wine pH, has been used, is the main mechanism of bentonite fining. So we use bentonite, which is a negatively charged clay, so it exchanges cations with proteins, and so sodium or calcium trapped in the bentonite matrix are released and are substituted by the positively charged proteins, which then is dragged to the bottom of the tanks alongside the clay. So this has been known. I mean, bentonite has been used since I don't know, 80 plus years in the industry, so this is not a news to us. And it has been so popular for so long because it's effective. It does remove proteins. It's fast. So the binding of proteins is quite quick. The settling itself can take longer for the bentonite to compound in the bottom of the tanks, but the actually interaction between protein and bentonite is really quick. We talk about less than a minute. But of course, a lot of research has gone into trying to find something alternative to bentonite because of the drawbacks that it has. So first of all, the bentonite produces lees, which depending on the type of wine and the type of bentonite, they can account for 3 to 10% in volume of a tank. So a lot of wine is trapped inside those lees, and then when you start recovering that, for example, through RDV filtration, the quality of the wine resulting is diminished. Bentonite cannot be recycled, so there are costs associated with its disposal. It is not specific for proteins. It is a charge interaction, and other molecules in wine are charged. So it doesn't just remove proteins, it can remove something else. In a winemaking setting, the logistic of preparation and additions are costly. So, you have to wait for the bentonite to swell and to prepare it, and there are dusts around. So there's also health and safety issues for the handling. Plus, you prepare bentonite in water, so you're actually adding water to the wine. That in some countries can be a problem because the wine dilution is regulated. So above a certain percentage of water cannot be added to a wine. So it has been calculated a few years ago that the wine industry spends $1 billion per year worldwide as related to the employing bentonite for protein stability. So the options for the industry are twofold. On one side, people can look at getting better bentonites, so to improve the efficiency, so using better materials or using it in a different way, like in a continuous system, for example. But on the other hand, we can also look for alternatives. We can look to find products or technologies that can replace totally, ideally, or at least partially, the use of bentonite. So as I was saying, if you want to improve the efficiency of bentonite, we can play with the type, with when it is applied, so juice versus fermentation versus in wine, addition versus separation methods. So there's been a lot of studies on inline dosing of bentonite with inline removal of bentonite via centrifugation, and also to understand if the tests that we're using are too harsh, if we can get better tests that predict better the need for bentonite to stabilize a wine in order to reduce the amount of bentonite used. But a lot of R&D has gone into finding alternatives, and the main areas that people have looked at are using proteolytic enzymes, so degrading proteins with our enzyme, so a targeted solution, alternative finding agents, or trying different processes. So among the alternatives to bentonite that has been studied and different levels of development, let's say, but in the past 15 years or so, these are the main ones that have been proposed. So in terms of finding agents, we have seen proposal of the use of Carrageenan, Zirconia, and more recently magnetic nanoparticles, zeolites, kiting, addition of tannins, and so on. There are many that have been proposed. A big sector of the research have focused on the development of proteolytic enzymes, so on the study of how proteolytic enzymes can solve this issue. And others, which has to do mostly with processing techniques, looked at destabilizing the proteins. So using heat, for example, we've seen that above a certain temperature, the protein, they unfold, and this unfolding can be irreversible. So you can get rid of proteins by making them unfold, by pasteurizing, by using microwave technologies, high pressure treatments, pulse electric fields, and so on. So this is another big areas of research right now that is looking at solving or finding alternatives to bentonite. So I'm going to show you the most representative, if you want, or maybe the most advanced alternatives that have been developed to date. So an interesting one, this is a paper from the Australian Wine Research Institute published in 2019, looked at using something which is quite similar to bentonite. So natural zeolites. So they are sodium and calcium aluminum silicates. As bentonite, these are also negatively charged at wine pH, but they do not have this shrink and swell behavior that is peculiar of bentonite. So there's some advantages on that area. This data come from this publication of the WRI, as I said, and they consider 3 wines quite rich in proteins. This is the milligram per liter. You go from 103 to 182. And upon heat test, they produce a net turbidity between 26 and 30 NTUs. So quite unstable white wines. These wines were treated with different bentonites, so 2 types of bentonites and 1 of natural zeolites. And these are the grams per liter required to reach stability. So you can see that wine A, one bentonite performed better than bentonite 2, but natural zeolites could also reach stability, also for B and C. So it is something that works, but as you can see from this data, it works at addition rates that are significantly higher than bentonite. So the advantages that the researchers have proposed or have hypothesized is that you can reach stability of wine. A good advantage is that you have a lower lees, so lower amount of wine trapped on lees because of the lack of swelling behavior of zeolites as opposed to bentonite. So that in the cost analysis, that is quite important. And as a side effect, you also remove potassium, so it can be good for helping in cold stabilization and pH management. For the disadvantages, the clear one is the higher amount required to reach stability, even though as bentonite, probably also here there's room for improving, room for looking at different materials or modification of zeolites to make it more effective. And as many of these alternatives that I'm going to show you, there's always to be considered the cost. So the total cost, including wine trapped on lees, the application, the cost of the product, the cost of disposal, and cost of handling, as well as the OIV approval, whether that is approved from the OIV or not, because many countries this is required for this product to be, for the possibility to use this product in wine. So another material which has been studied is Zirconia, which is a Mesoporous materials. There are others also that have been proposed, but other Mesoporous material because of the characteristics of these types of materials. Basically, the wine can be trapped, the proteins in the wine can be trapped in the Mesoporous, in the porosity of these materials, which can be made, can be custom made to increase this basically ability to bind to protein. So these have been trialed by a variety of researchers, including myself, and the best result we had was to use it during fermentation in a pellet form. So you can get this these small discs of Mesoporous zirconia with a very high surface of exchange. And the way we did it in a small scale was to dip this in sort of a tea bag, so that we don't need to add them and remove them. We just let it in during fermentation by exploiting the natural movement of the wine. So the CO2 produced by the yeast making a wine circulation would allow for a good contact between all the different parts of a tank and the material. We saw that the fermentation rate went better with these tea bags with zirconia inside. We saw that by adding zirconia, in this case, the third day of fermentation, we saw that a very fast drop in protein content. You can see this is the total protein content of that wine. So you can see that we reach a wine which is which has much less protein than the wine untreated. There is no lees production as opposed to bentonite or zeolites, as we've just seen. So this is a big plus for its use in the cost analysis. And we didn't, upon sensory analysis, find any significant sensory or compositional change. Very interesting, this is easy to regenerate, just wash with some sodium hydroxide, commonly used in the winery anyway. It could bring it back, and so you could remove basically the proteins that are sticking into the mesoporous part of this material and do it again. The negative side is the addition rates. Again, high dosage is required. It also was shown to remove some metals, which can be a negative. In some cases, it can also be a positive, but it depends. So there needs to be wine movement. So during fermentation is okay because the wine movement is natural, but if it happens in different stages of winemaking, in the juice, or before fermentation, or in the wine after fermentation, then stirring will be required for the removal to happen successfully. Another alternative, which is more of a fining agent in this case, is Carrageenan, which is a cell wall polysaccharides extracted from red seaweeds, widely used in the food industry, but not only. So there's Carrageenan as a thickening agent used in many industries. And some types of Carrageenan are negatively charged at low pH. So as bentonite, as zeolites, they can bind grape proteins when added to wine. So this is already used in beer for protein stabilization as well as copper fining for a while. So you have these seaweeds negatively charged which can interact with the positively charged proteins. There were some studies done, and we saw, again, this is the total protein content of different wines. In this case, there are several. And you can see it, the starting wine, the control in green, and in blue you have the Carrageenan treated wine. So you can see that in every case, the amount of protein left in the wine after treatment with Carrageenan was very, very small, and this leads to a stabilization of the wine. When the proteins are removed, there is no instability anymore. So it's very effective in removing grape and wine proteins, and it will show a low sensory and chemical impact. There was a bit of an issue of overfining here because Carrageenan that does not interact with proteins stays in the wine, and is a polysaccharide that if you do a heat test gives a false positive because it causes some turbidity if you heat it up. So there's also a problem in here, mostly with the fine tuning of finding the right rate of addition to stabilize a wine that doesn't go over that, because the wine wouldn't pass a stability test anymore if you put too much Carrageenan, because itself it would cause a turbidity upon heating. So another study, a recent study from the LabRide, and there's these 3 papers that came out on this topic in the past 4 years, is related to the use of magnetic nanoparticles. The proposal here thinks it's very different from the one that we've seen so far. Here they took magnetic nanoparticles and they coat it, so they functionalize it on the surface, this magnetic nanoparticles, so that they would be reactive with wine protein, so they could bind them. So if you add a nanoparticle that can selectively bind wine proteins and is magnetic, then that can be removed using an external magnet. So you don't have to filter or to do or sedimentation to try to remove it. So it is an interesting idea using magnetic nanoparticles that has been already developed for other fields of application. So you get your proteins being removed from the wine alongside the nanoparticles quite easily. So it has been shown by the results on this paper that is an effective and quick protein removal technique. There's a minimal production of lees. Potentially there is the possibility to detach the protein from the nanoparticles and reuse it. And it has been shown that to be quite selective, so minimal impact on wine composition. The negatives is the concern for potential residues of nanoparticles in the wine, of magnetic ones. So being so small, they can maybe not be fully removed. So something is to be said about this. The OIV will need to approve it, and we are not. I don't think that the process for this has started yet. The costs that would diminish if they could be reused, but the cost seems to be quite high. And also the application rates is quite high to reach a significant decrease in instability potential of wines. So it's something which is being developed, but it will take a while, I think, to become more ready to be used. An additional proposal that also came in the last couple of years is the use of grape seed powder. So some researchers propose to use as a fining agent grapeseed powder that was roasted at under 80 degrees for 10 minutes. So you roast it, you modify the structure, you ground it in a fine powder, and you add it to grape juice to remove proteins. Of course, proteins are, I haven't said that, but proteins are by nature, are by nature protein binding agents. So being grapeseed powder rich in tannins, what you're adding actually is tannins bind into proteins, so forming an insoluble aggregate that can be removed. The pros of this technique is that it was shown that you can partially stabilize the wine, not fully, at least not in the couple of papers that have been published so far. And the other one is that you valorize a waste product, so a byproduct of the wine industry, which finds a new utilization which can add value to the chain. The negatives is that the doses required have been seen so far have been quite high. We talk about 20 grams per liter, which is a large amount. And the sensorial effects is still quite unknown. The second study reports on some sensory aspects, but there's still more to be done in this area to see if this becomes a viable solution, a viable alternative to bentonite. So I keep this as a last type of last family, if you want, of solutions, which is proteases. Proteases would be the ideal solution. Enzymes in many other steps of winemaking are used successfully because of their targeted action. So if you have an enzyme that targeted degrade the protein, that would be ideal because you wouldn't have side effects that most of these solutions that I've shown you so far would have. The problem is that due to the characteristic of proteins that I explained the first part of the presentation, it is hard to degrade wine proteins, especially at winemaking conditions, so low pH, low temperature. Proteases normally don't work well at low pH, don't work well at low temperature, so they would require a different pH, a higher temperature. Plus, the PI proteins are a tough set of molecules to degrade because they are globular, so they're difficult for the enzyme to find access to a point to be able to destabilize and degrade them. So there has been some studies, and here is a paper from Van Slyter in 2013, in which they show the Botrytis cinerea, so a fungal that can grow and attack grapes in the vineyard, is able to actually secrete a proteases, which was named BC, so Botrytis cinerea aspartic protease 8, BCAP8, which was effective against chitinases during juice fermentation without heating. So this is a chromatogram. Each peak is a protein. It's an HPLC separation. You can see this is the thaumatin live protein peaks. So the control in blue, another enzyme control, that an acidic enzyme pepsin, which you don't use in wine anyway, degrades partly, but the BCAP purified would be able to degrade half of the thaumatin and also more than half of chitinases. So this results in less protein in the wine and, of course, less turbidity upon heat test. So it's at fermentation temperature. So this was done at 20 degrees. But still not sufficient to fully stabilize a wine. So the idea, which comes from the study of the mechanism of formation, is to, because we know the proteins are globular and they are robust to proteolysis, but we know that proteases will be able to work if the proteins are in unfolded state, so they're more accessible. They lose their globular shape. By using a combined strategy in which we submit to heating the wine or the juice, in this case, the proteins, they will unfold, so they will be more accessible. And if we have a proteases that we add when the protein is unfolded at higher temperature, this can work well and degrade it in peptides. So this is the rationale of a study we've done a few years ago, in which we flash pasteurized juice, not wine, to avoid the negative effects of heating a wine, especially the potential loss of fermentation aromas. So we did it on juice pre-fermentation, and we flash pasteurized it for a minute at 70 degrees in presence of a food grade aspergillopectins in small quantity. And this worked really well. We had that only the heat unstable proteins would be degraded because 70 degrees is higher. Sorry, I don't know what's happened. It would unfold only the PR proteins, but the invertase and LTP, so the stable one, will still be folded. So the protease will not degrade stable proteins. So you actually selectively remove some proteins. Which is an advantage because proteins like invertase can add some sensorial characteristics to the wine, especially in sparkling wine when you have foaming, they are foam stabilizers. So this mechanism didn't show a sensorial difference if you compare with a wine stabilized with bentonite, and it's cost effective because you don't produce lees. The negatives of this approach is that a pasteurizer is needed. The OIV needs to approve it, even though we are at an advanced stage of approval in this case. And also the heat test needs to be updated, because if you only remove the unstable proteins, sorry, I don't know why this keeps doing that. If only remove unstable proteins, that means that the wine which you produce in this method will still contain a little bit of invertase, a little bit of LTP. And if you do a heat test on a wine containing some stable proteins, chances are that you will get a bit of turbidity, not because that those proteins will destabilize over time, but because you do destabilize them by heating them up at 80 or 90 degrees. So heat tests will need to be slightly modified to account for this. So very recently, a paper just published this year proposed a combination of protease, heat, and ultrafiltration. So it's a kind of a development on the project I just shown. But basically, they decided to, instead of treating the whole thing, so the whole juice, to treat only a portion of it. So they propose ultrafiltration, so membrane technology to separate the molecules bigger. So if you pass through a filter of 10 to 20 kilodalton, basically proteins are bigger than this. So what goes through this molecule to this membrane will be wine protein free. And what is retained by the membrane can be concentrated. It's called retentate. And if you only treat the concentrated full of protein wine in this case, with the heat plus enzyme technology, you can partially reach stability in this case, partially reach stability by treating only a portion of the wine, so by not affecting aromas in the whole volume. So the study showed that a partial wine stabilization could be reached with limited wine compositional changes and low impact on volatiles, lower than eating the whole wine. The disadvantage is that you need to add an extra piece of technology, so membrane technology, to separate by ultrafiltration, OIV approval, which for the enzyme part, which is still needed, plus the sensory and cost side of this are still unclear. It's the first paper that comes out. Probably there will be some follow-up on this later on to see if this is becoming viable option or not, because of some side effects. So to conclude, this is a few take-home messages. So we know there's been a lot of development on understanding the mechanism of haze formation. And this is being exploited by R&D working in this sector to improve, on one side, the bentonite efficiency, so that we can decrease the side effects associated with its use, but also to propose new strategies for wine stabilization. So of the many promising alternatives, I didn't show them all, but the most promising, at least in my opinion, some of those, like grapeseed powder, zeolites, are at the very early stages of development. So there's been maybe 1 or 2 papers coming out. So a lot of ground needs to be covered to see if they will become a real competitor to bentonite. Some, like Carrageenan magnetic nanoparticles, have been studied more. So the development is more advanced. We can talk about intermediate stage. So with more R&D, they might become viable in the future. But the one that is at the final stage is the one involving proteolytic enzymes associated with heat. This is currently being looked at from the OIV for its authorization, the enzyme part. So this seems to be the most advanced of them all. But that's all from me. I thank you all for your attention. Here's my email address and my Twitter handle if you have some question later. And thank you very much.